Thank you very much, Thomas, for the introduction. This is work that I've done with Azim Chadwari, who's sadly left me to get a proper job in industry. So he confessed that this might be his last paper on static analysis, which is a shame. Okay, now sometimes we end up doing research that we never really intended to do. It was never quite the plan, and this is a paper like that, and we decided to sort of share our experimental work on implementation, because this is not a paper about a novel abstract domain or a framework. This is a sort of very focused paper, and it's really an implementation study, and no more than that, but we think the results are quite surprising. Okay, so I was chatting to Anton over the break, and I said, did you ever expect your work on Octagons to have so much influence? And he sort of shrugged in a very sort of Gaelic way and said, well, no, not really. But of course he was being very humble and very polite. You know, his work on Octagons, and we all know this, has had great impact and influence because the domain operations are polynomial, and they have real elegance, and it's one of the few domains that we could hand to a capable undergraduate, and they could implement it and get it right. And that's one of the real strengths of this domain. And in terms of expressiveness, although the domain is conceptually simple, we can get a surprisingly long way with it. So with the Octagons, we can bound variables, we can express lower bounds and upper bounds on variables. We can express differences between variables, and we can put upper and lower bounds on sums of variables. Okay, so the Octagon domain is really like differences on steroids, and it gives us an extra degree of expressiveness, but we don't have to pay a big penalty in terms of cost. And the sort of usual way now to implement these things is to resort to an encoding where we work with an augmented set of variables. So we take our program variables, we add a set of negated program variables, so we work over two n variables rather than n variables, and then we use off-the-shelf machinery from solving difference constraints, and we work over DBMs, and that all works great. Well, it sort of works great because it's sort of well known that there is this rather frustrating or perhaps annoying thing about doing verification with Octagons, and that is when we work over rational numbers, the performance is not as good, in fact, nowhere near as good as when we work over doubles. Okay, and the usual school of thought is that what we do is we're going to, sacrifice the precision that comes with working with rationals, and we're going to, because we want the precision of double precision, because we want the speed that comes with floating point numbers. And these are numbers here that were that was the running time of various benchmarks of various sizes, and here we were using the EVA plugin of the Frama-C system. Okay, so I think the sort of interesting thing is the thing which I put in the bold cells is there's typically an order of magnitude difference between floating point numbers and rational numbers. And that's quite surprising, really. And we sort of looked a bit about we looked a bit about what was going on here, and this is typically when we're working over larger DBMs. So there's a performance hit there that we found rather unsatisfying. Okay, so what do we try to do? And this is like a tale of woe that like motivates the work in a way. Is that what we thought we'd try and do is that we would look at this like poor relative of abstract domain operations, which I think of as being the incremental closure operation. So there's lots of stuff on join and meet, but incremental closure operation is this operation that when you've got a DBM that's closed, okay, you add one or two constraints and then you reclose, and this is an operation that's called very, very frequently. So high frequency operations, so you want it to be efficient. And what we did is we looked at the existing work on the incremental closure for DBMs, and we thought we'd done very nicely because we sort of had a reformulation of incremental closure that was amenable to parallelism. So we thought parallelism was a way of dealing with this performance hit, because what we'd do is we'd execute our rational operations in parallel, and therefore we would match the performance on doubles, and that would be great. Well, that was fine. We did the theoretical work, we proved correctness, and we even came up with an algorithm that was like a racy algorithm that required very few locks. We went to implement it in EVA, in EVA, and the performance was very disappointing. And we couldn't figure out why for a very long time. We assumed it was because of an interaction between OCaml and our domain operations that were implemented in C. We assumed that's where the problem was. And after a certain amount of time, we thought, okay, we just better do some profiling just to check where the time was going. And Core Grind, to our surprise, found that EVA was spending a very large amount of time doing a very simple operation. We should have done profiling straight away. Okay. Core Grind revealed that 36% of the calls came from one operation, and that's the operation QM PQ int, and all that does is allocate some memory for a rational, and then initialize that memory. Now that's absolutely crazy. So we thought the thing to do was to remedy this problem, and then we might be able to observe some speed ups using our algorithm, because this overhead was dampening the performance of our enhancements. Okay, so that's what we set out to do. Okay, and that's where this work really starts. So, we've all seen BDDs, and the reason why BDDs are successful is that BDDs exploit common structure. Okay, so what you do with BDDs is you don't pay the penalty for representing the same tree many times. What you do is you represent the same subtree just once and use hashing to exploit that. And we thought that was perhaps something here that could be done for DBMs. What we could do is that we could detect if we've seen the rational before, and then we could squirrel that rational away in a table, and then in the DBM, we would not have a DBM of rationals, but we'd have a DBM of just short 16-bit identifiers that would direct us to a table, and then we'd read the rational from there. So that would give a denser representation, and that would work if we didn't have many rationals, distinct rationals, that occurred over the lifetime of an analysis. So we implemented this technique, and to our surprise, we found that there were very few distinct rationals that occurred even over the lifetime of a very long-running analysis. There might be 100, there might be 200, there might be 1,000, but even if you had like 100,000 DBMs, there'd just be a few distinct rationals. So this seemed to be a win, and I'll talk about the numbers that we get later on. So just to summarize here, if we had a DBM like this, and DBMs have this strange like zigzag-like shape, and all these elements here represent numbers, what we do is replace these rational numbers with identifiers to the rationals in a sort of number pool, and we always ensure that we have this symbolic value infinity in a number pool. So it's a very simple idea. Goes back to the 50s. There's barely any novelty in this, but it seemed to work. Okay, well, we thought that was cool. Okay, so let me just talk you through what happens if we take, the beautiful closure operation, which is like a Floyd-Warshall operation, and we just see that we see this extra layer of indirection that we sort of lay on top. Okay, so this is the closure operation. As I said, we work over not over n program variables, but 2n program variables, because we work over an augmented variable set. And what we do is we have 3 nested for loops, and this is the beauty of closure. It's no more than this. Okay, and closure is the operation that puts octagonal constraints into a normal form. We need to do something else, but that operation is quadratic, thanks to the work of people in this audience. And what we essentially do on each operation is just find shortest paths, and we route through intermediate nodes. So that's all we do here. Okay. So when we want to overlay this sort of classic approach, and M here is DBM with our what we are calling compact DBMs. Okay. what we do is we take the heart of this algorithm, which is this minimization step, okay, and what we do is we take the matrix C, which is now a matrix of identifiers, okay, we look up the value that's associated with a particular element, say Cij. This then gives us a rational, okay, then we use this to do our math, which is here just a min and a sum, okay, then we get a new rational, and then we have to decide if we're going to store this and in one sense make it persistent by putting it in the DBM, okay? And that's where this extra search step comes in. So there's extra computation involved here. This is not free. So what we do is we take our new rational and we ask ourselves the question, is this a rational that we've seen before during the lifetime of the analysis, okay? So we have two like memory operations, okay, and we represent these as functions. These are functions which are duals of one another. And what we do is we ask the question, have we seen this before? Okay, so we have this function search, and that maps a rational to its unique index. Okay, so we say, have we seen this rational before? And if the value is not in the domain of search, if it is in the domain of search, we simply return that identifier, and then we store away that identifier in our CBM. And if it hasn't been seen before, then we generate a new identifier. Okay, we extend our domain of values, which maps identifiers to particular rationals with this new value and this new identifier, and we do the dual thing for our search, and then we return our new identifier, and then search returns with this new identifier, and we use that to update our new form of DBMs called a compact DBM. It's very simple. Okay. Well, we use this to get some performance improvements that I'll talk about shortly, and that was enough to sort of finish off the FMSD paper, which was good. And then often when you sort of finalize the submission, you think, oh, right, okay, there's something else that we could have done. And we realized that although this work was intended as like a memory optimization to improve the amount of memory we use, and in fact to improve the cache behavior as well, we realized that it allowed certain tricks to be applied, which were very simple. And I'm going to talk you through these very simple refinements today. And this is the first one. We can optimize the closure operation by just introducing a guard, a check, okay? And what that does is that as part of the closure operation, what we do is we enforce the property that the identifier for the symbolic rational infinity is always fixed, okay? And we're going to call that fixed value, that fixed identifier, L infinity, okay? So what we can do is that when we go to calculate our closure operator, we can check very quickly with just by comparing to 16-bit values, okay, to see if the cell that's represented at Cij corresponds to infinity. And if that is, then we can bypass the inner loop of the closure operator. And this is not a deep idea, but I think the nice observation is that here we're not operating on a numeric value, we operate at the level of the identifier, just to bypass the loop. Okay, that's very, very simple. Okay, now perhaps a more important question is, can we do this in incremental closure? Because incremental closure is called more times. And this is our sort of take on incremental closure. If you look at it carefully, you can see there's quite a lot of parallelism that's exposed here. So we've got a loop here over I and a loop j. We've got some temporary values, t3 and t4, and then we've got a min, this time not over 2 values, but 3 values. So the idea was that we can execute these two things in parallel, and we can also carve up the loop over I and j and do that in parallel as well. That was our intention. But we can apply the same trick. What we can do is that when we read things from the element, we can check to see if the identifier corresponds to infinity. And if we do that, again, we can bypass bits of the incremental closure calculation. So what we're doing here is that, if you like, we are retaining the structure of closure, but we're getting some of the benefits of a sparse representation because we can just jump over bits of the computation, which we know will not update any values because they're operating over symbolic values of infinity. It's a very simple idea. Now you can probably guess what's coming next. Join. You can do the same thing with join as well. So what's nice about closure is it puts the DBM into a normal form, and that allows you to calculate closure on two BMs in a sort of pointwise way. So that gives you a very simple construction for closure. So in the classical interpretation, what we do is we look at each element of the two DBMs, we take the max, and we put that away in the join. And what we can do here is do a very similar thing. Okay, we can look at one element, and we know that if one element there has the identifier which corresponds to infinity, irrespective of what the other element is, we have to then store away in the compact DBM the identifier for infinity. Okay, what's more, if the two identifiers are the same, then again we don't need to look at any rational at all. We can squirrel away the value for one of those identifiers. And it's worth pointing out that the cases here that I've marked in red are the dominating cases. Okay? So in the calculation of join, it's quite unusual to actually have different elements in the DBMs. So we exercise a more general case very seldomly. So again, we speed up join very significantly. And we can do a similar thing for meet and a similar thing for widening. Okay, well, let's go further. There are other things we can do as well by exploiting this representation, and we can think about how we actually realize search. Now, our first attempt at this, our first shot at this, was to use, was to actually search for the rational that was when we were looking for the identifier that corresponded to a rational. What we did is to use bisection search. Okay, but if we had like a number pool of, say, 256 rationals that we'd have to search, then if we were using bisection, we would then do possibly 8 comparisons, okay? And each comparison with 2 rationals would itself reduce to 2 multiplications. So in the worst case there, we'd be doing 16 multiplications, okay? And we don't want to do that. So what we did instead was to think about using hashing. Okay, so we take our rational, and in the GNU multiple precision library, what you can do is you can convert a rational number to a floating point value. Then we calculated the hash quickly by operating over floating points, and then that gave us a hash for looking up finding our rationals. So what we did here was to use nothing more than a golden ratio hash. So we take our rational number, we convert it to a float, and if if S is the size of a number pool, we then multiply that, the F and the S and the golden ratio to get a number. We convert to an integer, and then we use that to index our hash table. And that gives us a very simple, very lightweight technique of then searching to see if we've seen this rational before. Okay, so that's what we did. All these are very simple things, and I think it's worth pointing out that the Octagon domain, is a success because it is so simple. So we didn't want to overload the Octagon domain with optimizations which were not simple. Okay, that would not fit with the ethos of the Octagon domain. Okay, so here are some numbers here, and the rest of the talk is just a series of tables and a series of graphs. Okay, so this is the function analyzer that was mentioned earlier today, so it infers piecewise ranking functions, and this graph here is, I think it's over 68 different benchmarks, and it compares the performance of DBMs over rationals to DBMs over doubles, and then CBMs over rationals to DBMs over doubles, okay? And the thing I want you to observe is that the triangles correspond to co-DBMs over rationals, okay? And this line here corresponds to this XY line, and you can see that the numbers are being pulled down here to the XY lines, the numbers are almost comparable. And you may wonder what's going on in that very dense corner over there. So we can zoom in there, and we can see that we get the similar sort of speed-ups again from moving from DBMs to co-DBMs, which is a start, but these are sort of short-running benchmarks. So this is not really where it's at. Okay, let's do something else and look at the SV comp problems, because there's quite a lot of these. There are hundreds of these, and there are essentially 3 product lines. So we've got 3 different types of benchmarks here. So we've got about 600 benchmarks here. And what we've done is we've sort of numbered all the benchmarks, and we calculate the cumulative time as we go across the bottom. So by the time we got here, this point here corresponds to the cumulative time of the first 300 benchmarks. Okay, so let's just take it from the top of the graph down. The dashed line at the top corresponds to Apron DBMs over rationals. Okay, and these are the times with all these optimizations and refinements applied. If we go down, we get the dotted line here. And what is that? Well, that's co-DBMs over rationals. So we can see we get a good performance improvement here. Next, and this was a big surprise, we get Alina over doubles. And I'll talk more about that in a moment, because we didn't expect this at all. Then, the next fastest, we got the solid line, that's DBMs over doubles. And finally, which is another surprise, we get co-DBMs over doubles. So this method also, these techniques also have the potential for speeding up operations on doubles, which is also not the intention, but is quite a nice byproduct of the work. Now, we were slightly freaked out by the fact that Alina wasn't working as fast as we expected. Okay, so we, in a rather paranoid way, we sort of checked all the settings. And since the paper has been accepted, Gagnan Singh has confirmed that the flags are okay. And what he suggested is these SV comp benchmarks mainly exercise incremental closure, so perhaps they're not showing the Alina work in its best light. And he's also suggested that the Alina only applies vectorization when the DBMs are dense. And our DBMs here are populated by lots of infinities. So I think this might be a worse case for Alina, which is unfortunate. And I don't want to say any more, because we're still looking at that, because I don't like to critique other people's work when I don't understand it fully. But anyway, I think those results are quite surprising. Let's go on. Here are some larger running benchmarks here. And this is now running in the context of EVA, the EVA plugin. And if you look at the second column here, these are numbers for the numbers of distinct identifiers that occur over the running time of the analysis. So these numbers are very small. We don't get very many different rationals, which is why this method works well. It's very surprising. These are numbers for Apron, and then we've got a whole series of numbers here which represent the refinements, and they sort of build on one another. So firstly here, these are the numbers here for when we use rationals and we look things up in a number pool using bisection search. And we know that has a performance hit because we're doing lots of multiplications. But nevertheless, that improves on Apron reasonably significantly. If we change the search method to hashing, we get a further performance improvement. If we add the join refinement, we get another performance improvement. And if we refine close as well, we get another performance improvement. Okay, so the point is these optimizations are very simple, but cumulatively they come together and we end up with quite a significant performance improvement for those benchmarks that work on larger DBMs. So these are very small changes in the algorithms, very small, literally just adding guards. Cumulatively, they have quite a big impact. And I think that's quite nice. Okay, this is now the numbers on doubles, and here the numbers are a bit more sordid, I'm afraid. So if you look at Apron on doubles, if you go to this bisection method, then we get a performance reduction, if we're looking at TAES here. But when we put them all together, we get a slight enhancement. The bad story is that we don't get a uniform improvement now, because if we look at Apron with bzip, okay, and we put all the optimization together, we're still running slower. So I think that says, really, you should not use CodeEMs for doubles. It's just not worth it. And sometimes things go worse. Okay, let's look at memory usage now. And I think there's an interesting story here. Okay, so here we compare Apron to CodeEBMs. And all these numbers are here, numbers in megabytes. And we harvested this information from the GNU time utility, because that gives us the maximum resident set size. Okay, so I think the thing to notice is that if you look at these numbers here, the amount of memory consumed is significantly smaller. And I think this could be important because ultimately what matters is your termination finishes. Okay, and reducing memory is the way to do that. What else have we got? We've got some numbers on doubles. We get a reduction here, but it's not very significant. A bit, but not very significant. And I think perhaps this is the slide which is the most intriguing slide. What we did is we decided to look at the cache behavior using cache grind. So those of you who've used cache grind will know that cache grind, it looks at the cache, it configures its cache to model it. 2 minutes, I've got it, Thomas. This will take 2 minutes. And then it gives you information of when you fell out of the lowest level cache. And that's the number of misses you do. And when you fall out of the lowest level cache, then you have to look up from something from memory, and that might take like 120 cycles. That really does kill performance. And the thing I want you to observe is that we significantly improve the miss rate. So let's just look at bzip, for example, okay? So A here is Apron. This is working over rationals. And here we've got 19 billion cache misses out of the lowest level cache. And we reduce that using this technique to 57 million. So we get 3 orders of magnitude decrease in cache misses. Okay. And that's good, just by these very simple refinements. Let me just close up now. Okay. So as I said, this is work we never really intended to do. It was experimental work that we ended up doing because we just applied a profiler. And the confession is that we spent months trying to figure out what was going wrong with EVA-C because we thought it was a problem with the threading. Okay, what we should have done is used a profiler straight away, and then the penny would have dropped. So there's a lesson there in methodology. If you get stuck in a program, use a profiler straight away. That's my bad. Okay, that's a sort of meta level that's a meta story on doing research. I think the messages to take away is that we've improved space consumption. That's good. We've bypassed a lot of arithmetic operations. That's good. We've saved work. We've improved cache behavior. That's good. And all we've done is this very humble thing of just introducing these checks to bypass ops and to use an idea that was known in the 50s. That's all we've done. And here I will stop.
Okay. Thank you, Andy. Questions?
Right, so initially, right, so you said that the very costly operation was MPQ init, right? And then I guess...
I'm having trouble hearing you.
Oh, sorry. Okay, so initially you said the costly operation was MPQ init, right?
Yes, that's right.
And so later you attribute the performance improved due to these extra checks against L infinity.
Okay, we've actually got 2 things going on. So we've got bypassing the memory allocation and initialization, and that's done by the use of the lookup table. So that's done by the bisection part or by the hashing part. And then on top of that, we've got these extra optimizations, which then improve things further.
Yeah, and I guess my question is, did you look up how much of the improvement could actually be attributed to that now it is very cheap to copy DBMs? Because copying is what the analysis do all the time, even when it's not necessary. And before, every time you copy a DBM, you initialize every element. And now your copy of DBM is just a byte-wise copy.
Absolutely. We didn't like cripple that operation to work out the cost of that. We just simply observed that now we can do a simple copy, and that's what we did without any more reflection.
Yeah.
Okay, I'm afraid. So I can't give you a number on that.
All right. Yeah, thanks.
Antoine.
So your optimization relies on the fact that there are a lot of infinities in your matrix. But if you analyze a program, the variables are bounded, even if it's max int or max double. So this tends to put finite bounds in all unary constraints that gets propagated into all binary constraints, and you don't have infinities everywhere. So how did you get so few finite bounds?
All I can say is that those were the benchmarks that we just used off the shelf. And we simply observed that these matrices were populated by infinity, and we didn't reflect on the fact that bounds were not being propagated into the matrix. And I concede that if you were propagating bounds from the size of the data types, then it would not be as successful.
Yes, and this is what we do in Astray. So
okay.
I'm a bit surprised that
perhaps it's no good
you
for
took
Astray.
3 different tools, very different tools, and they all do the same. So, okay, it's interesting.
Yeah.
Okay. Any other questions? So
just to reflect on that, there was at one point we thought of not just capturing infinity, but also capturing other symbolic constants, such as 0. But we didn't do anything with it because we did not want. We were fearful about introducing extra checks. So we wanted the checks had to be, super lightweight. So we didn't want to double the amount of checks.
okay. So do you want to make that confession, or?
Well, the confession was that we just wasted months searching for ghosts when we really should have used a profiler straight away.
Which profiler?
We used perf, and then we used call grind. And it was when we used call grind that we saw where all the calls were going. And I didn't even believe the numbers when Azim harvested them initially.
Okay.